Hello AP Physics 1 students. There's a problem we didn't get to because of the shortened block today. So I need you to have your Newton's laws problems in front of you and turn to problem number 3, which looks like this. This is what's called a statics problem, which, as we already talked about, is really just a fancy term for things that stay still. So here we have a system of strings connected, and from the series of connected strings, we have this sign here called a physics rock sign. And we're going to analyze this to figure out the tensions in all the strings, right? Anytime we know there's a string, there's going to be a tension force, and we're just going to use our knowledge of forces to figure out the magnitudes of the tensions in each. So we'll start with a free body diagram of the physics rocks sign. And of course we could do all the stuff off to the side, velocity, acceleration, net force, but it's pretty easy in this case. We know that since nothing's moving, since it's static, the velocity is 0, the acceleration is 0, and the net force is 0. So we just need to think, okay, so what forces are acting on the sign? And of course we'll start with weight, which of course we know points straight down. And what's supporting the weight? Well, there's a string there. So what sort of force in the string? It's tension. So this is not going to be complicated. We can go right ahead to drawing the free body diagram. We got weight straight down and the tension up. And here we're calling it T3 because it's in string 3. Just that easy, right? How much is the weight? We can do a quick calculation. The mass is given. Just do that real quick. So we see its weight is 4.9 newtons. And hey, if the sign is just sitting there and the net force is 0, how much is the tension? Well, you don't have to go through some fancy math and even setting a positive direction. You know the tension is going to support the weight. And so T3 in magnitude is equal to 4.9 newtons. And so we're really a third of the way through the problem, right? We just have to find the tension in 3 strings. So here we found the tension in string 3. It's 4.9 newtons. Okay. So now we have to analyze the other strings. And here's where it gets a little bit interesting because we still have to draw a free body diagram. But where's the other object? Well, it's here. It's the knot. So we're going to draw a free body diagram of the knot because that's where all the strings are attached. So go ahead and do that, considering that the knot is the object, and think about which way the strings are pulling on the knot. So pause the video and go ahead and draw your free body diagram. Okay, so before I reveal what it looks like, we just want to remind ourselves that, of course, the tension is inside the string, and strings only pull, as we said before, right? And so we want to imagine these strings are pulling away from the knot, and we can label the different tensions by their string number. So it should look like this. In string 1 is T1, in string 2 is T2, and string 3 is T3, and all those tensions are pulling away from the knot. So take a second and redraw your free body diagram as necessary. Okay, so the next thing we want to do is we want to analyze this in terms of combining the forces to get sigma F, but here we have the tensions being at odd angles to each other. So what do we need to do? We need to resolve into components. In this case, we're just going to resolve into strict vertical and horizontal components. That's the easiest thing to do. And so we're going to draw those components for T1 and for T2. Notice I always draw components in a different color, but even if you don't have a different color, you want to somehow offset them in some way. So I like to draw them as dashed lines because it's sort of imaginary. We're imagining we're taking T1 and replacing it with its components. We're imagining we're taking T2 and replacing it with its components. And these components should be arrows. They are vectors, right? If T1 is pointing up and to the left, notice that those arrows are pointing up and left. If T2 is pointing up to the right, its components are pointing up and to the right. It should make sense. Okay, so at this point, I'm just going to use our trig functions here to take the 30-degree angle. The vertical component here is opposite, so we're using sine. The horizontal component is adjacent, so we're using cosine. Same deal here with T2. So we can calculate it. Even though we don't have the numbers yet, this is going to help us in our analysis. We'll shift the diagram over there, and off to the side, we can make a two-dimensional chart. Find some space on your page where you can do this, nice and big. And here our dimensions are vertical and horizontal. So we're just looking at it from the side. This is easy. First thing, of course, is to assign positive directions. That's completely arbitrary because the whole system is at rest. There's no preferred direction. So arbitrarily, I'll say up is positive for the vertical and to the right is positive for horizontal. But honestly, it really doesn't matter if you want to try it with other positive directions. As long as you're consistent, you'll get the same thing. So, of course, we know motion in one dimension is independent from motion in other dimensions. So we write sigma F equals ma on both sides. And since this is a statics problem, we know the acceleration is going to be 0, and so the net force is 0. So we start on the horizontal side with sigma F equals 0, and we add up all of the horizontal forces. So since I called right positive, we can say T2 in the x direction, that's right over here, is positive, and T1 in the x direction over here is negative, and they have to add up to 0, which means T2x equals T1x, or replacing them with their trig function counterparts, T2 cosine 50 equals T1 cosine 30. Hopefully this makes sense to you because these horizontal forces have to cancel. Just imagine if they didn't, what would happen? Well, that would mean that one of them would win over the other and the knot would accelerate. And since this is a statics problem, that doesn't make any sense. So of course the horizontal components have to balance out. So here we have one equation with two unknowns, clearly have to keep going. So now we go to the vertical side, and again we start with sigma F equals 0. Now looking at only the vertically pointing forces, with up being positive, we have T1 in the y direction, that's over here, that's positive, and T2 in the y direction, that's also positive, and pulling away from the knot, we got T3 pulling down, that's going to be negative. So we replace these with their counterparts with the trig functions, and also recognize that we already know the value of T3 from before. We know it's going to be 4.9 newtons, so we have T1 sine theta plus T2 sine 50, T1 sine 30 plus T2 sine 50 equals 4.9. In other words, the two vertical components of the tensions here and here have to balance out the downward pull of the tension there, which really comes from the downward pull of gravity. But it is tension. It's not mg. It is tension here because it's a string pulling down from the knot. All right, so what do we do now? We've got two equations and two unknowns. It's clearly a solvable system. It's just from here on out, the algebra gets a little bit hairy. So what do? Well, you have to solve one of the equations for one variable and substituting the other. So my suggestion is taking this equation over here on the horizontal side, solving for either T1 or T2, and then substituting it in to the equation on the vertical side. So I'll show what that looks like, but it really doesn't matter which one you do. So for example, let's say we solve the equation on the right for T2. So it's T2 equals T1 cosine 30 over cosine 50. And we just take this expression for T2, drop it right in here where we see T2 on the vertical side. So there it is. Right? This expression right here is T2 from the horizontal side, replacing T2 in the equation. And don't forget, we still have sine 50 on the right there. Now we have only T1 as the unknown variable, so we can pull T1 to the outside. Oh, apologize. I want to go back a second. I forgot about combining the trig functions. Right, here we have sine 50 over cosine 50. And if you know your trig identities, sine over cosine is tangent. The cosine 30 is still there, but sine of 50 over cosine 50 is tangent of 50. Okay, so now we have just T1 as the variable. We can pull that to the outside. Everything else remains inside. That's a sine 30 plus cosine 30 tangent 50. And what do you do now? We're just going to divide by this whole business here and move it over to the right-hand side. So it's a little bit messy, but that's it. It's just pure algebra. So at this point, you can put the numbers in and go ahead and solve. You'll get an answer for T1, which hopefully is very close to the answer on the problem there. And then take your value of T1 and put it back in here for T2 and solve it that way. Again, a lot of this is just algebra. And on the AP exam, they never actually asked you to solve a statics problem like this in full. They have asked you to set up the equations. And really, that's where the physics comes in. So the physics here is looking at the picture, doing a free body diagram, making sure your forces point the right way, realizing you have to resolve the components, and using your trig to figure out which function goes with which, setting positive directions, writing sigma F equals ma for both directions, sigma F equals 0, combining forces with our positive direction, combining forces with a positive direction, and from there on out, it is just algebra, which of course you're all good at. And yes, the algebra is a little bit much, but certainly nothing you can't handle.